Okay, good morning. Just going back to what we have from the Test 4 Review Part 1 handout and looking into logarithms. And we have, in the case of number 12, okay, now we made the transition from expanding logarithmic expressions to combining. And in the case number 12, now this is a little bit of a trick item. And in this problem, okay, we have 12 times the base 5 logarithm of the cubic root of y minus 4 plus 2 times, okay, the base 5 logarithm of the quantity of y squared plus 15 minus 5 times the base 5 logarithm of the cubic root of y plus 5. And just looking at taking what we have here and combining as a single base 5 logarithmic term. What I can do at the moment, okay, is that, okay, for this problem, with the first and the last terms, I can just convert the radicals as non-integer powers. Okay, so we have with the first term just doing a rewrite. Okay, so I have 12 times, okay, the base 5 logarithm, okay, and the cubic root of y minus 4. We will have a y minus 4 quantity to the 1/3. Second term, now I could go ahead and write the 2 as a power, but I'll just do this in the next step. Okay, so again we have 2 times the base 5 logarithm of the quantity of y squared plus 15. Then we have minus, okay, 5 times the base 5 logarithm. And for the cubic root of y plus 5, okay, just like with the cubic root of y minus 4, I'm going to quantify the inside binomial in parentheses and say that that expression is to the 1/3 power. And so just looking at what we have here, okay, now in the expansion, okay, I had rewritten powers as coefficients, and in the case of combining logarithmic terms in the same base, I'm going to go in the other direction. Okay, so we have for 12, I can make that into an exponent, likewise with 2, and also with 5. Okay, now for the first term, okay, now we got the base 5 logarithm. Okay, now y minus 4 is already raised to the 1/3 power. Okay, and you can say that 12 is going to amplify the situation. Okay, so here we have the base 5 logarithm. Okay, and we already have a y minus 4 to the 1/3, and this expression, okay, this will be further raised, okay, to the 12th power. And we have plus, okay, the base 5 logarithm of y squared plus 15. Okay, this will already be to the second. And we have minus, okay, the base 5 logarithm. Okay, and again, we already have y plus 5 to the 1/3, but this will be further taken to the 5th power. All right, so we have in the rewrites, okay, so we have the base 5 logarithm. And again, with the power property of exponents, you have a base to a power raised to another power, and the powers will be multiplying each other. So 1/3 of 12 is going to be 12/3, which reduces to 4. So we have the base 5 logarithm of y minus 4 taken to the 4th. Again, I have the base 5 logarithm of y squared plus 15 raised to the second. And we have with the last term, okay, so we're going to have, again, it should be base 5 logarithm, okay, and we have y plus 15 to the 1/3, then to the 5th power, again, taking the power property of exponents. So we had taking the property of the, or the product of the powers, okay, so this is going to be the quantity of y plus 5 to the 5/3. All right, so we have the coefficients converted to exponents, and we have with the attachments, okay, the attachments of positive logarithmic terms, okay, those will go in direct terms, and where we have fractions, those will go to the numerator, whereas those negative terms where we have division to be implied from subtraction, okay, the attachments of negative logarithmic terms, okay, those will go on the bottom. So looking at consolidating, okay, so you have a base 5 logarithm, and just looking at what we have here, so we have y minus 4 to the 4th, okay, this stems from a positive base 5 logarithmic term, so this attachment goes in the numerator. And then we have the square of y squared plus 15. This stems from a positive base 5 logarithmic term, so this will also go in the numerator. And for y plus 5 to the 5/3, this is attached to a negative base 5 logarithmic term, so this will go in the denominator. Okay, so this will be your final answer, and if this could be displayed in any other fashion, you could write the non-integer exponent terms along the lines of radicals. Okay, so the way that you could express this, okay, so we have base 5 logarithm we have y minus 4 to the 4th times the square of y squared plus 15. And for the quantity of y plus 5 to the 5/3, you could write this as the cubic root of y plus 5 to the 5th. And if there were any other way, okay, it'd be like to multiply everything in the numerator, like y minus 4 to the 4th, y squared plus 15 squared, but I would not recommend that. Just leaving in factored form will suffice. Okay, now for what we have going back to exponential equations, okay, that will share a common base, and we have for number 13, okay, we have 8 to the x plus 6 is equal to 4 to the x. And this is an example of an exponential base that shares a common base. Now, the common base we do not have up right yet. Okay, now 8 is a multiple of 4, but it is not an integer power of 4. Okay, like what I mean by integer power of 4, okay, like 4 to the 0 is 1, 4 to the 1st is 4, 4 squared is 16, and I've already passed 8. Okay, and so just rewriting what we have with 8 and 4 along the lines of a common base that is shared, and that's going to be a number that will multiply itself into both 4 and 8, and that number is going to be at 2. All right. So taking what we have here, okay, for 8, 8 is going to be 2 to the 3rd, since we have 2 times 2 times 2 to be equal to 8. Now for 8 to the x plus 6, okay, this is going to be, in terms of base 2 for right now, you got 2 cubed raised to the x plus 6 power. And for 4 to the x, now 4 is 2 to the second. And for 4 to the x, okay, we have, right now we have 2 to the second and then raised to the x. And again, just dealing with the power property of exponents. Okay, so again, for a base to a power, we're going to have taking the product of the powers. So you have 2 to the 3 times all of x plus 6. And for 2 to the second to the x, okay, this will be 2 raised to the 2 times x power. Okay, now we have, again, this is a common mistake that many can make for like 2 cubed to the x plus 6. They'll see the immediate interaction between 3 and x and just go ahead and say that the result's going to be 2 to the 3x plus 6, and they neglect to multiply 6 also by 3, or a case like it. Okay, so whatever is going to be the power outside the parentheses, again, everything, whether it's a single term or a multi-term expression, it's going to be multiplied by the inside power. So not the result what we have with 2 to the 3x plus 6, but 2 to the 3x plus 18. So we have 2 to the 3x plus 18, and we have is equal to 2 raised to the 2x. And now we have single base 2 terms. And now we can set the powers equal to each other. Okay, so I have 3x plus 18 is equal to 2x. And I have 2x by itself, and so I can just move the 3x by subtracting. And so we have the 18 is equal to negative x, and just changing the signs. Okay, so we have for the missing value in x, okay, that is going to end up at negative 18. Now, for what we have in the case of number 15, okay, so we have 1 over 1,000 raised to the x is equal to 10 raised to the 1 plus x degree. Okay, and we have for this one. Now the common base we already have present. Okay, so you have CB for common base. Okay, and again, that value is going to be at 10. Okay, and we have this base on the right hand side of the equation. Now for 1 over 1,000. Okay, now 1,000 you have both to be a multiple and an integer power of 10. So now 1,000 is going to be 10 raised to the third, since it takes 3 tens to multiply out to 1,000. Okay, so I have 1 over 10 to the third is equal to 10 to the 1 plus x. Now the right hand side of the equation, I have the base 10 expressed in direct terms, but on the left, okay, I have the reciprocal of this base 10 term. So if I write this in direct fashion, okay, and just kind of going back to rule of thumb here, and we have with the inverse property of exponents, like a to the negative x is going to be the reciprocal of a to the positive x. Well, guess what? I got 1 over 10 to the positive 3. And if I rewrite this, okay, that is going to be 10 to the negative 3 power. Okay, so 1 over 10 cubed raised to the x is going to be 10 to the negative 3 raised to the x. And I have equal to 10 raised to the 1 plus x power. And we have with the power property, we're going to have 10 to the negative 3x equal to 10 to the 1 plus x. And we have single base 10 terms. Okay, and so this will give us the green light to go ahead and set the powers equal to each other, and thus set things up where we can now go ahead and solve for x. So now we have negative 3x is equal to 1 plus x. And negative 3x is by itself. And if I combine that with the subtraction of x, okay, so we have negative 3x minus x becomes negative 4x. And we have that negative 4x is equal to 1. And we're going to have with division by negative 4, it's going to result that we're going to have a negative fraction, which in this case x is going to be equal to minus 1/4. And let me give you a case here. Now, so far we had, with 13 and 15, we had single terms on both sides of the equation. And give you just an added example where we are looking at solving for x. We might have more than one term on either side. And let's say if you're looking at solving for x, and we'll say that we have here, let's say we have something like 3 to the 2x. And we'll say we have times 9. Raised to the x minus 2 is equal to 27 raised to the 3x. Okay, and so for what we have here, okay, so you got 3, 9, 27, and again we have the common base to already appear, and that common base is 3, since 3 will multiply itself into both 9 and 27. And so if I convert the 9 and the 27 in terms of base 3, okay, so the leading term, okay, we still have at 3 to the 2x. Now, for 9 raised to the x minus 2, now 9, again, that is going to be 3 squared. And 9 to the x minus 2, that is going to be 3 squared raised to the x minus 2 degree. For 27, okay, 27 is going to be 3 to the 3rd. And 27 to the 3x, we have right now 3 cubed, and then you have raised to the 3x degree. So for right now, we got 3 to the 2x. Then you have times 3 to the 2 times all of x minus 2. And we have equal to 3 to the 3 times 3x. So you have 3 to the 2x times 3, and 2 over the quantity of x minus 2. That is going to be 2x minus 4. And we have equal to 3 raised to the 9x. Alright, if you notice, we have all these terms in the rewrites, and also with the removal of the parentheses. Okay, we have base 3 terms. Okay, now I have a single base 3 term on the right, but I have these two on the left, and I want to make into one. So we're going to use the product property of exponents, and this will call for adding these powers together. So for the product of what we have with these base 3 terms, we have 3 to the 2x plus 2x minus 4 is equal to 3 to the 9x. And so for what we have on the left, we have 2x plus 2x is 4x minus 4. Again, we have equal to 3 to the 9x. And so we have single base 3 terms now, and we can set the powers equal to each other. So we have 4x minus 4 is equal to 9x. And with 9x by itself, I can join this with 4x by subtracting 4x on both sides. And so we have that negative 4 is equal to 5x. And if I divide by 5, okay, we'll have for the resulting value in x, we have once again a negative fraction, whereby we have that x is equal to minus 4/5. All right. Now, so I just wanted to put this up, okay, in case you have more than one term on either side of an equation where we have a common exponential base, and this is such a case here. Now, for what we have in the case of working with money matters, okay, and we have in the case of number 25, okay, we have looking at compound interest and future value. And okay, case A, you have non-continuous compounding, whereas you do have it for case B. And it says here to find the future value of $3,000 invested at 10% compounded. Okay, in part A, we're looking at monthly after 6 years, and part B, we're looking at continuous compounding. And for what we have here, in the case of number 25, okay, and we have just for the input information, okay, so we have that P is equal to $3,000. And again, we have the rate of interest. Okay, we'll have it 10%. And converting to a non-percent decimal case, you have 0.1. And for the time span, okay, so we're looking at 6 years. All right, and for what we have in the case of part A, again, we have with the future value compound interest formula that is non-continuous. Again, we have P times the quantity of 1 plus R over N raised to the N times T power. Okay, so we got the P, the R, and the T. And now we're going to have the N is equal to 12 since we are looking at monthly compounding. So looking at filling in the known quantities or the given quantities. Okay, so you have P is at $3,000. And we have times quantity, so we have 1 plus R, so we have, okay, have 10% or 0.10 or 0.1, and we have over N, okay, so N is at 12, and for N times T, okay, so we got 12 times 6. And for the values that we have for the sum and also for the exponent, okay, so you have for 0.10 over 12, okay, so you will have a very small decimal value to be added to 1, and the sum in this particular case, right, we'll have like 1.008 followed by 3's that are going to repeat. So just keep that display. And we have raising to the 12 times 6, or 72nd power. And still waiting to multiply by $3,000. And we have with this decimal value to the 72nd power. Okay, so we have 1.81759. And just keeping those digits and multiplying by $3,000. And we have in terms of currency, okay, this will come out to right at $5,452.78. And again, this is what we have for monthly compounding with the circumstances, okay. And again, for part B, we're crossing over to continuous compounding, okay, where n is going to be heading to infinity, all right. And the more frequently the compounding is done with the same given conditions, okay, we'll anticipate an even higher future value, okay. And so just looking at what we have with part B, again, so you have continuous compounding, so this 1 plus r over n to the n times t, okay, that's going to become e to the rt. So with continuous compounding, the future value that we have at p times e to the r times t, and again, e is that natural logarithmic exponential base value, which we have is that 2.718 number. And looking at filling in for the principal, the rates, and the time. Okay, so again, we have for P, okay, we have a $3,000. And for e to the r times t, so r we have at 0.1. And the time span again is going to be for 6 years. Again, you're going to multiply r and t. Okay, so 0.10 times 6, so that's going to be a 0.60. And for $3,000 times e to the 0.6. And for e to the 0.6, okay, that number is also going to be over 1.8. Okay, and just for my display here, so you've got about 1.8221188. And just taking what we have here and multiplying by $3,000. So at 10% interest, that is compounded for 6 years with $3,000 put in, the theoretical maximum future value, which will be from the continuous compounding, okay, it's going to be right at $5,466.36. Okay, so compared to the monthly compounding, okay, you're looking at somewhere between $13 and $14 greater. Right. Now, for what we have in the case of the next items, now these formulas that we have with future value, those are concerning one-time investments or deposits. And now for 26 and 27, these are going to be in reference to repeating deposits on a regular basis. And for this particular topic, okay, this is going to be what we refer to as annuities. Now I'll show you a couple of formulas here, okay, and the traditional annuity formula, okay, this is looking at the conservative side of things, and from first glance, okay, I guess you can say there'd be quite a bit of repetition. But for what we have here, okay, say we have for a recurring deposit, that occurs let's do a little bit of color coding here. So you have that occurs n times a year. At the end of each cycle, and we have into an account. That draws interest. And again, so you have n times a year as well. So you have the deposit frequency and the compounding frequency to be the same. Okay, now we're going to have the future value. Will be the following, okay? And the annuity formula is going to look like an amalgamated version of the non-continuous future value formula for compounding interest, and in a sense it is, because before with this formula we had, this is for a one-time deposit, but for just like a consistent lump sum of deposits, this would be like if you're looking at just putting aside so much money, say like every quarter, every month, for financing, for a down payment for a home or appliance or an automobile. Okay, we have with this formula, okay, you have A is equal to, again, so you have P, and we have times the quantity. Okay, we have, again, so you have 1 plus R over N to the N times T, and we have minus 1, and then you have times N over R. Okay, and okay, so this is going to be your annuity formula. Now, and let's say that if we have, as an instance, okay, just as an example, okay, okay, and we'll say that we have, looking for the future value, okay, say we have P is equal to $300. put in at the end of each month. Now we'll say that we have for the rate of interest, okay, so you have R is equal to 6% and is a non-percent decimal. Okay, so we have 0.06, and we'll say that, okay, time span is going to be for 5 years. And since we're looking at putting in $300 at the end of each month, so you have a monthly cycle, and we'll have the compounding of interest to be done on a monthly basis. And again, so we have for this particular formula, okay, so I'm looking at finding out what A is going to be. Okay, so you have P at $300. That's what is put in, okay, at the end of each month. Okay, we have with the numbers, okay, so you've got 1 plus R, we have at 0.06. And we have N at 12. And for N times T, okay, so you have 12 times 5. You have minus 1. And we have times N over R, okay, so that's going to be 12 divided by 0.06. Okay, so you have these values already put in. So now we've got $300. And looking at the activity within the brackets, okay, so you have for the quantity of 1 plus 0.06 over 12. So you have 1.005. And this will be to the 60th power. You have minus 1. And 12 divided by 0.06, okay, that number comes out to a whole number, which we have at 200. Okay, and still working with what we have inside the brackets. Now we have with 1.005 to the 60th. Okay, so that number you have over 1.3, and among the first digits you have 1.3, 1.34885. And just keeping what we have here and taking away 1. And we're getting closer to final value here. Okay, so for the difference, okay, I'll just kind of put this on full display. So you got 0.34885. $0.1525 times, okay, 200. Okay, all right, and let me just mention, okay, so this is what we have in the big picture. Okay, so we got $300 at the end of each month, and you're doing this for 5 years. So you're looking at like putting away, okay, $3,600 a year for 5 years. So that's going to be $18,000 worth of lump sum deposits, okay? And the rest of the future value is going to come from the interest, okay, which is compounded monthly at a rate of 6%. And so just putting this all together, and it's going to turn out that the future value is going to be at $20,931.01. So you have $18,000 in the lump sum deposits and the 293101 will come from the interest that is accrued. All right. Now, okay, so this is for what we have at the end of each cycle. Okay, but let's say that if you have, hypothetically speaking, okay, an opportunity for one to do like theoretically the most proactive investing imaginable. Okay, and we have just, so I'm just going to take, so just for these parts here, and just change the terminology. Okay, now for what we have here, okay, let's say that instead of at the end of each cycle, if I have recurring deposits to be at the start of each cycle, and we'll just use almost the exact same example. Okay, whereas, you know, instead of having like $300 put in at like the end of the month, we have it like put in at the start of the month, like the first of each month. We have R at 6%, so we still have at 0.06. T is for 5 years. Okay, and we still have N equal to 12. With the monthly compounding. Okay, now you will still be putting in the same amounts. Okay, but for what we're going to have this time around, okay, for the start of each cycle, okay, there's going to be a change up, and it's going to be the slightest of modifications. This formula, again, this is for the end of each cycle, and this is your traditional annuity formula. And the slightest of modifications. You got your annuity formula, and then if you had the most proactive depositing done, you can have the annuity formula, the conservative one, times just this factor, and this is just going to be 1 plus R over N. Okay, and so looking at what we have with $300 put in at the start of each month, okay, we had this 1 plus R over N factor to consider. Okay, so we have with 1 plus R over N, so we have 1 plus, and R we have at 0.06 over N, which is 12. And again, you're going to have that 1.005 again to reappear. And the difference between what we're going to have in this example and what we had before with the end of the month investing is going to be this particular factor. So what I mean by this is that with this formula, again, I have the number 1.005. And again, the balance I had before with the end of the month investing had $20,931.01. So the difference between the start of the month and the end of the month is going to be just this lone factor. And so we have a little bit of a difference here. And this balance, okay, this will come out to right at $21,035 and about 67 cents. All right, so those are just a couple of quick cases of annuities. Okay, one of which we have with the end of the month cycle, and the other where we have at the start. Now, for what we have in the case of numbers 26 and 27, and we have here, okay, we have Ray, who plans to retire in 15 years, and it says that he contributes $1,000 to an IRA on a semi-annual basis. And it says here that the rate of return is assumed to be 10% compounded semi-annually. And we have in the two scenarios, it's asking what would the minimum value of the IRA be when Ray retires. Okay, that is if he invested at the end of each 6-month cycle. You have in part B, if Ray had invested at the start of each 6-month cycle, what would the maximum value be? So you have like in part A, you're looking at like maybe at the end of June and the end of the year with the investments, whereas you have that with the maximum, you have like maybe it's close to January the 1st and July the 1st, okay, where you might have a bit of a difference in both cases. And now for what we have in the case of 26 and 27, and what I will do here, okay, just to kind of cut down on the scrolling, see if I can. See if I can find this. No, that's not it. Oh, here we go. Okay, so we got in Ray's situation. Okay, so we have for number 26, part A. Okay, so you have P times, okay, the quantity of 1 plus R over N to the N times T minus 1. You have times N over R. So just putting in the numbers. Okay, so we have, so he's contributing $1,000. Okay, so P is at $1,000. We have times the quantity now we have for 1 plus R over N. Okay, so rate of return you have at 10%. So 0.10. N, okay, you have semi-annually. Okay, so semi-annually. Okay, that means that N is equal to 2. And we're looking at twice a year for 15 years. We have minus 1, and we have times N over R, so N is at 2. Again, we have for the rate of interest, okay, we have 0.10 from 10%. Okay, so we got with the numbers. Okay, so we're looking at $1,000. okay, times the quantity. So 0.10 over 2 added to 1. Okay, so this is going to be 1.05. And 2 times 15 is going to be a 30. Yeah, minus 1. And 2 over 1/10. Okay, this is going to go to 20. And looking at what we have for the numbers. Okay, so we have inside the brackets. So you have 1.05, okay, to the 30th, okay, and for that particular figure, okay, we have okay, just over 4.3. We got minus 1 and have times 20. And we have in the follow through. Okay, so you have this number minus 1, and for the difference, you have among the digits, you have 3.32, 19423. You have times 20, so multiplying your decimal result times $1,000 times 20. And for the future value at the minimum, okay, Ray is looking at around $66,438.85. All right. Now, in the case of what we have for part B, okay, it's the same scenario, but where Ray is investing at the start of each 6-month cycle. And again, the difference, okay, is going to be the factor, which we have 1 plus r over n. Okay, so everything from p times what's in the brackets times n over r. I got that part from part A, and the difference with the theoretically maximum attainable amount, you have this factor 1 plus r over n. So again, we have r at 10%. And you have, again, semi-annual compounding and depositing. Okay, so the 1 plus r over n, okay, that's going to be 1.05. So we have for A, we have with 1 plus r over n, so you're going to have 1.05. And we have times what we had in part A with 66,438.85. And this time we'll have, okay, like just over a $3,300 difference. Okay, so there is a kind of a significant difference here. So with the more proactive side, okay, you have the difference between the theoretically maximum and the minimum. Okay, you have like going from 66,438.85 to, again, the maximum attainable, which we have right at $69,760.79. Okay, so for number 26, you're looking at future value. Now, for what we have in number 27, Now this is kind of going in a reverse direction. Same formula, but where the future value is already provided. And for 27, okay, we have for a child born this year, a 4-year college education at a public university is projected to be around $170,000. And assuming a 5% rate of return compounded monthly, about how much must be contributed to a college fund every month in order to have $170,000 in 18 years. It says, notice, okay, we are using this formula and are solving for P, and whatever result we have, okay, it says you're going to round up to the next penny in your answer. Like if you had, like the outcome to be like 33.1 cents, you're going to round that up to 34. Okay, so we have, in the case of 27, okay, so again we have this formula. Again, just sort of working in reverse. Okay, so we got, it is A that is at $170,000. And the rate, okay, we have at 5%. And we're looking at monthly payments. And also where the compounding is done monthly. Okay. And the time span, again, we have 18 years. And we're looking at solving for P. Okay, so just filling in the numbers. Okay, so you have with A, we have $170,000. Once again, we were looking at solving for P. And for 1 plus R over N, so you have 1 plus 0.05. And you have over 12. And for N times T, so you have 12 times 18. You have minus 1. Okay, and for times N over R, okay, so you have N is at 12. And for R, again, we have at 0.05. So you have, again, 170 grand is equal to P times, and we have with, while we have inside parentheses, now we have continuous running the decimal places, and for what we have in the mix, okay, so you have 1.004, 1, okay, and you have sixes that will repeat, and we have rather large exponents, so you have 12 times 18 becomes 216. We got minus 1. Now 12 divided by 0.05, okay, that will be at 240. Then we have within the parentheses, so you have this decimal to the 2/16. You have among the first digits, so you have 2.455. And again, we have minus 1. And we have times 240. And for now, so we got P, and we have for the difference in the brackets. Okay, so I'm just going to write this out. Okay, since we're looking at breaking it down to pennies. So 1.455008423. We have times 240. Okay, so for the product of the decimal result and 240, okay, so we have 349 points. So we have 202.0215 times P. Okay, and if I divide $170,000 by this decimal, so for P, okay, so we're looking at $486. And then for the change, okay, again, we have 0.8242. And again, I'm looking at rounding to the next penny. Not the nearest, but the next. Next one on up. So for what we're going to have here, so you have $486, and what is going to be 83 cents. Okay. So we have with this particular financial arrangement. Okay, so someone puts in 486.83 every month, say like at the end of the month. Okay, like doing this every month for 18 years, where interest is compounded monthly at 5%. Okay, it's like after that 18-year cycle that they will have a grand total of right at $170,000. Okay, so just another case of an annuity, but where we were looking at solving for the present value or the recurring deposit amount. All right, now just going back to exponential equations. Now the ones we started out with had a common base. Okay, but let's say that if we are looking at exponential equations that do not have this feature. Okay, so if we have exponential equations with no common base, and we'll do here, okay, is that going back to our earlier properties of logarithms. Okay, we had the base A logarithm of a to the x is equal to x. And also we had that the base A logarithm of m to the r, and that is equal to r times the base A logarithm of m. And again, we have with the change of base formula. Okay, so the base A logarithm of m, again, you had your secondary base, like base B logarithm of m over that of a. And again, that secondary base you can either have as natural or in terms of the base 10 logarithm. So for exponential equations that have no common base, and let's say that if we have looking at solving for x, and we'll start out with, say, the variable on one side of the equation. And we'll say we have, first of all, okay, we'll say that we have 4 to the x is equal to 39, okay. And just in terms of approximating, okay, so you have 4 to the x is equal to 39. Okay, so you have like 4 to the first is equal to 4. And we've got 4 squared is equal to 16. And we have 4 cubed is 64. Notice you have 39 is going to be somewhere between 16 and 64. So you're looking at 4 to the 2 point something is equal to 39. So it's going to be a number greater than 2 but less than 3. So looking at what we have now with 4 to the x equal to 39. And if you notice, we have the variable x on just one side of the equation. And so I can free up x from the exponential base 4 by taking this property where you have the base a log of a to the x is equal to x. Well, the base a here is going to be 4. Okay, so we can take a base 4 logarithm of both sides. So for the base 4 logarithm of 4 to the x, okay, this will go to x, and we have x is equal to the base 4 logarithm of 39. And now, again, so for the base 4 logarithm of 39, okay, now, chances are your calculator will not have a base 4 logarithm, but it will have a natural or base 10 logarithm. And if we go with the change of base formula using the natural logarithm as the secondary base, so we have the natural logarithm of 39 over the natural logarithm of 4, and we say that to about the nearest 4 decimal places. That 2 point something is going to be at right at 2.6427. Right. And let's say that if you have a situation where the exponential base is going to be higher than the constant to which the exponential expression will be set equal. And let's say if we have something like 100 to the x is equal to 15. Right, just sort of cue you in. Okay, if you have like a non-zero number to the 0 power, okay, that is going to be equal to 1. And just like 100 to the 0 is a non-zero to the 0, so that is equal to 1. And we have 100 to the first, that is equal to 100. Now, in the case of 15, we have like 100 to the 0 point something, some number greater than 0 but less than 1 is equal to 15. Now, for what we have in the case of 100 to the x is equal to 15. Again, so we have the base a is going to be at 100. So I can take the base 100 logarithm of both sides here. So we'll have x is equal to the base 100 logarithm of 15 And if I utilize the change of base formula, I can either go with natural logs again or base 10 logarithms. And I'll go with log this time around. So we're looking at the base 10 logarithm of 15 all over the base 10 logarithm of 100, and it's going to follow that. For what we have here, x is going to be right at 0.588 if you take it to around the nearest 3 decimal places. And one might think, well, why is it 1/2 in degree when 15 is a lot closer to 100 to the 0 than it is 100 to the first? Well, if you think about like 1/2 degree is like the square root. Say if you have like 100 to the 0.5, that's going to be the square root of 100, which is going to be at 10. So that kind of changes the dynamic in terms of like one might be thinking of in terms of interpolating. And 15 is a number greater than the square root of 100, or 100 to the 1/2. So that number is going to be greater than 1/2 for what we have in x. All right. And now, so this is a case of what we have with x on one side of the equation. And let's say that if we have a situation, and this is going to be about like pulling teeth, but I know that there's been like a problem in Alex to arise, where you're looking at the variable to appear on both sides of the equation. And you're looking at, say, if you have solve for x, and you're looking at rounding the answer to the nearest 4 places. Now, say we have, in this problem case, say we have 18 to the x plus 2 is equal to 22 raised to the x minus 1 degree. And what I'm going to do here is going to copy these items. See. That didn't quite work out. Okay, so you have the base a logarithm of a to the x is equal to x. Again, you have the base a logarithm of m to the r is equal to r times the base a logarithm of m. Okay, so if I had x on just the left-hand side, I could take base 18 logarithms. And if I had x just on the right-hand side, I could take base 22 logarithms. But there's not an advantage in using either of these. And to make the interaction with the calculator a bit quicker, you can either take the natural log or base 10 logarithm on both sides. So for what we're going to have here, so we'll go with log on this one. But it could be ln. So you have log of 18 to the x plus 2 is equal to log 22 to the x minus 1. All right. And in terms of what to do now, okay, so we got this property, okay, where the exponent can be written as a coefficient. So here we have binomials with the exponents. And setting things up, okay, which we have here. So we have the quantity of x plus 2 times, okay, the base 10 logarithm of 18 is going to be equal to x minus 1 times, okay, the base 10 logarithm of 22. And I'm going to do here, okay, I'm still solving for x, and I'm going to have a couple of x terms. And I'm going to go ahead and distribute. So just separating, okay, so you have x times the base 10 logarithm of 18 plus 2 times the base 10 logarithm of 18 is equal to, and we have with the distributing, so we have x times the base 10 logarithm of 22 minus the base 10 logarithm of 22 Okay, notice we have a couple of x terms with logarithms attached, and I'm going to join these together. So I'll just take away x log 22 and I'm just going to move 2 times the base 10 logarithm of 18 by subtracting. Okay, so we're going to have in the rewrite, okay, so we're coming down to the difference. Okay, so you have x times the base 10 logarithm of 18 minus x times, okay, the base 10 logarithm of 22 is equal to the negative the base 10 logarithm of 22 minus 2 times the base 10 logarithm of 18. Now for this difference here, I'm still solving for x. Now I'll go ahead and factor this out. So you have x times the quantity of the base 10 logarithm of 18 minus the base 10 logarithm of 22. And we're just about there. Okay, so I'm going to divide by this difference. And what's going to happen here is that for x, I'll just go ahead and put in the calculator notation, so I have minus log of 22 minus 2 times log of 18 Okay, so just use color coding, to emphasize the importance of the grouping symbols. Okay, and we have over the quantity log of 18 minus log of 22. Okay, and so we have for x, okay, just taking what we have now, went a little bit over, sorry for that, but here we have 44.2107 for the final result. So again, be careful with the grouping symbols, especially if you have like binomials divided by other binomial expressions. So just encapsulate with the parentheses.